Okay, here we go. Get your notes out. Okay, we got to talk some math here. So, where we left off, this would have been for, what's today? Tuesday? Friday. So we were going through and we were going to try to derive a rule for taking the derivative of a power function, right? So we got to kind of look back at our notes here a little bit. So if f of x is x to the n, we're just going to apply we're going to start with our general limit form of the derivative, and we'll apply it to our specific function, right? So we got f prime of x equals the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0, like the limit of the difference quotient as delta x goes to 0. And then if we apply our function, if f of x is x to the n, f of hand is hand to the n, so f of x plus delta x is x plus delta x to the n minus x to the n over delta x. And here's where we had to get a little bit tricky. So we did, I believe, we used Pascal's triangle, right? Rather, we could have just pulled up the formula for the binomial expansion, but we used Pascal's triangle. And we came up with a general formula for the nth row in Pascal's triangle, right? We saw that the pattern was, at least for the first few terms, then it gets more complicated. For the first few terms, the first coefficient was n, was 1, then we had n times n minus 1 over 2, and then they progressively just got more complicated. But we didn't need all that stuff anyway, because when we do the expansion then, we end up getting x to the n, 1 times x to the n, plus my next coefficient is n times x to the n minus 1 delta x to the 1, right? Remember that the powers of x are going to decrease from n incrementally by 1, and the powers of delta x are going to increase from x to the 0 incrementally by 1. So the sum of the two exponents, I've got a delta x to the 0 there, don't I? The sum of the two exponents is always going to be n, right? N plus 0, n minus 1 plus 1, n minus 2 plus 2, etc. And just all the way on out to the very last term, which would be minus, or the very last term of our expansion would be delta x to the n, right? There's a whole bunch of terms there. How many? N plus 1, right? We don't even know, we don't have to pin n down, it could be anything. And then we're subtracting our x sub n at the very tail end of all that stuff. And so what we saw then is we can cancel the x to the n's. All of the remaining terms have at least one delta x to the 1 in them, right? Here we have a delta x squared, delta x cubed, all the way on out to the final term would be delta x to the n. And so when we do our limit then, we could factor a delta x out of the top and cancel that with a delta x on the bottom, and then that first term is the only term that doesn't end up with a power of delta x still attached to it, right? So in the limit that we let delta x go to 0, all of the other n terms are going to vanish, and that first one is the only one that sticks around, right? And so we come up with an answer. We come up with the derivative of x to the n is n times x to the n minus 1. So what's our rule then? What do we do if we're given something like the derivative of x to the 7th? What do we do? So if we apply that rule to a really simple one, if
7x to 6.
Okay, right, so if f of x equals x to the 7th, f prime of x, the rule for differentiation, the power rule, whatever the exponent is, you just bring that out front and you subtract 1 from the exponent, right? Easy. Okay, that's our rule.
So that's why x squared, f prime of x squared is 2x.
Yeah, the derivative of x squared is 2x, right? And it works for everything. It works for constants too, right? The derivative of 7 would be the derivative of 7 times x to the 0. So if I pull that exponent out front, what do we get? 0, right? So it works all the way down the line. Okay, let's expand this just a little bit though. Let's look at another issue here. What if we take f of x just equals c times x, where c is a constant? And I'm picking a specific function, but we wouldn't even have to pick a specific function. We could just leave it as f of x equals c times g of x or something. We'll get the same result. Look what happens if we do the math here, right? If we take the derivative, right? So we start with our limit of the difference quotient, as delta x goes to 0. F of x plus delta x would just be c times the quantity x plus delta x minus c times x. And if I distribute, everybody agree, if I distribute the c, and the cx's are going to subtract away, I'm just going to get c times delta x over delta x. Delta x's cancel. And I just get my answer equals c times 1. Okay, what's the moral of that story? The limit of, had I not had the c there, wouldn't I just have got an answer of 1? So what is that telling us? This is just one example, but it tells us something pretty important. What can I do if I have taking the derivative of some constant times a function? The constant just doesn't, we can just keep that until the end and multiply it by the answer, right? So in this case, you know, the derivative of, if we just took f of x equals x, well, the derivative of x just became 1, but then we've got this c that we multiply by the answer, right? So the moral of the story there is that we've got this, where'd it go? Well, I guess I never wrote it down. What was I doing? Not sure what I was doing. Anyway, there it is right there. That's what we wanted to get to. Right. So this is just a constant rule, right? Constant multiplier rule for derivatives. What that tells us is if I'm taking the derivative of a constant times a function, the best way to deal with this algebraically is to take that c and just pull it out in front of the derivative, right? So in other words, if we take an example like what if we had f of x equals 7 times x squared, right? What could we do? We would just pull the 7 out in front of the derivative. If I want to calculate f prime of x, that's just 7 times the derivative of x squared. And this notation is going to look a little weird. I'll talk more about notation in a second, but what this is telling us to do is take the 7 out front and just take the derivative of x squared, right? Pull factor constants out in front of the derivatives and leave them there until the end. And then you just multiply them through. So this would give us a what? What's the derivative of x squared? 2x. So we just get 7 times 2x equals 14x. Okay? So we can combine the two things then. We can combine the two things into a more generalized power rule. Okay? Where if we take the derivative with respect to x of some constant times x to the n, we just lump the n out front with the c. It always works that way with any constant. Don't make too much of that. I mean, it's anything profound. Okay, so let's practice that a little bit. So let's just look at some examples of that one simple rule. That's really powerful. Yes, ma'am. Sure. Okay, I'll put these up. The notes are up already from. No, the test. Everything's up in calculus. All the videos and the notes are up. I'll put this up right after school. Okay. Yes, sir.
So the exponent for x7, for x to the 7 is becomes 7x to the 6.
Right. When you differentiate, the derivative of x to the 7 is 7x to the 6.
The exponent always has to add up to what the factor outside is.
So whatever, if you're taking the derivative of a power function, you always just, whatever the exponent is, that becomes the coefficient, and you drop the exponent down by 1.
So it always has to add up. If you add 7 back to the 6, then you can 7. Not like 7 plus 6, but like 7 is a factor.
Right. That whatever's there always ends up there.
Right.
Yeah, exactly. Yeah. If there's already a constant there, then you just multiply whatever that other constant was by the exponent. Okay?
So,
Okay.
in the part where it says times 2x, we got that on the x squared, right?
Where are you looking?
Bottom right.
Bottom right, yeah, exactly. Right. We got 7 times the derivative of x squared is 2x. So really, in your head when you're doing this, all you would do is you would say, okay, I'm going to bring the 2 out front. 2 times 7 is 14, x to the 1. You do it in one step. Okay? All right, so notationally, what are different ways to say derivative? These all say exactly the same thing. Why do we do it so many ways? Contextually, sometimes one makes more sense than the other. So if we're starting with the function f of x, then we could say the derivative is expressed as f prime of x. We've already done that one quite a bit. If we're starting with maybe something like y equals some function, then we can write this as dy dx, right? So for example, if I have y equals x squared, what's dy dx equal to? 2x. That's just saying the derivative of y with respect to x. Okay? We could also say, if we do something like y equals x cubed, one shortcut would be to say y prime. Just another way of saying derivative. What does that equal?
3x squared.
3x squared. Okay? Another way of doing it would be to say if we want to just not explicitly write the function first, and you've seen me do this, we could just do the derivative with respect to x of like x to the 4th. So that means that acts like an operator. So we're doing this operation to that function to get a derivative. So what's the answer? Good. Okay. Specifically, if we write it like this, we would read this as dy dx. And what it means is what all these mean, which is the derivative of, in this case, y with respect to x. That's how we'd say that.
On the bottom, is it supposed to be dy over dx, or y is just 2?
Which one are you looking at?
On the very bottom.
So that one's just so the way we would say this would be the derivative with respect to x of x to the 4th. Okay.
Why isn't there a y next to the?
Because we didn't define this as y. We're just saying this means we're gonna differentiate.
No.
So that means we're gonna take the derivative. When I just have derivative with respect to x of something, then whatever's inside there is what we're differentiating. Okay. So those will all pop up in various different places. They all mean the same thing. Okay. Sometimes, like this makes a lot of sense if we're talking about the relationship between functions and their derivatives, right? Because then the prime just tells you literally that we started with f of x, and we changed it a little bit, right? We derived a new function called the derivative from that function. Okay? This one makes a lot of sense if you're talking about maybe derivative as a slope, right? Because it looks like delta y over delta x, looking at the rate of change of y with respect to x. Okay? And we'll talk a lot more about rates in the near future. So let's do a couple of these. Let's do some tricky ones. So these are all going to be examples of that simple power rule that I just gave you. Okay, but what's important to do here is I call it, a lot of times textbooks will say rewrite. I always call it pre-write, because before you even do the calculus, you're going to rewrite the function in a way that fits our derivative rule. So what's our derivative rule again? The derivative with respect to x of what? What's our power rule? Like, which one did we just talk about? Okay, so we can include the c if we want to. Cx to the n equals
C and x to the n minus 1.
Okay, so that doesn't look like a power rule problem. What do I need to do to rewrite that in a way where it looks like something that fits that form?
X to the negative one.
There you go. Okay. I could just rewrite this as 2x to the minus 1, and now it fits. Right? Eventually, you won't have to, you can do that in your head maybe eventually, but for now, you want to always write these out explicitly in the way that matches the derivative rule. Okay? So what's our answer then? What's dy dx if that's y? Negative 2. I got to take the exponent times whatever's out front times x to the negative 2. Negative 1 minus 1. So if we want to write that maybe in simplified form in terms of positive exponents, that would just become negative 2 over x squared. Right? Okay, how about questions? Okay. Okay. Okay, how about that?
Is that X or T?
It's a t.
It doesn't.
I'm offended that my writing would be perfectly clear exactly what it means every time. So what are we going to do with that?
That's 4/5 times t squared.
Yeah, the 4/5 isn't doing anything, right? It's just a constant. 4/5 is just, that's the same thing as 4/5 times t squared, right? So you don't even really have to rewrite this, but if you wanted to, it would just look like 4/5 times t squared. So what's f prime of t going to be?
8 over 5.
Yeah, I'm going to multiply 2 times 4/5, so I'm just going to get 8/5 t. T is 1. Right? Okay, no biggie. All right, we good? How about that? What am I doing with that one? Somebody different, help me out. Who did? How am I going to rewrite that as a power, so I can use my power rule? X to the 1/2, there you go. So we can rewrite this then, now it looks good, right? If I've got 2 times x to the 1/2, what's y prime going to be?
1.
Good. Bring the 1/2 times 2 is 1, x to the negative 1/2. 1/2 minus 1 would be negative 1/2. And so that looks like 1 over x to the 1/2, which is just 1 over square root of x. Right? Right. I mean, you know, honestly, calculus people don't really bother with that very much. It's,
That's a more useful function.
I would prefer to leave it like that most of the time. I mean, I know that I always tell you to rationalize denominators, but you don't really worry about it very much.
Being calculus is consequential.
It's, yeah, it doesn't really do anything for it.
Again, drop boys on that on the exam though.
I'll look into it, but I don't think they would. I really don't think they'd take anything off for that. Almost positive. Okay, how about something like that?
Oh boy.
So how can I rewrite the argument of the derivative, what we're putting into the derivative? I'm going to pull the 1/2 out there, and let's just deal with that part inside. What's that going to be? So what is, if I, let's ignore the fact that it's on the bottom for a second. If I have a cube root of x squared, what is that as a rational exponent? X to the 2/3. The fact that it's on the bottom makes it negative. So what's our answer going to be then? So I'm going to get negative 2/3 times 1/2 is going to be negative 1/3, right? Times x to the negative 5/3. negative 2/3 minus 3/3, right? Minus 1 would be negative 5/3. So we could write that as negative 1 over 3 times x to the 5/3, or if we really wanted to, we could write that as the cube root of x to the 5th. But it's really fine to just leave it as x to the 5/3 on the bottom too. Okay? Okay? Make sense? So these all look pretty tricky at first, but if you're just clever about it and you rewrite the function to fit the form of the power rule, they all become pretty simple. Okay, what about something like this? This introduces a new rule to us. What do you think happens if we have multiple terms like that? Now think, and I'm not going to prove this to you. It's kind of a boring proof, and it doesn't really reveal very much. But think about this in terms of limits, right? Because derivatives are built from limits, so it just stands to reason that they inherit a lot of the properties that limits do.
You only have to use it.
Well, if we were doing like an infinite limit, maybe. But if we were just going to be taking derivatives, if we were going to take this derivative using limits, we would end up, would you agree, I'm not going to write all this out, but we'd end up with the limit of the difference quotient, but we take the limit of that term plus that term, but I could just split those up into separate parts, couldn't I? When I'm doing the limit? Would you agree? I could, if I wanted to, it was convenient for me to at least think of it that way, I could break it up into separate limits of each term. So what that means is I can differentiate term by term. Okay, so if I'm faced with something like a polynomial or something that's not quite a polynomial, but it's a sum of a bunch of terms, I can just differentiate each term individually, so it's really not a very complicated process. Yes, sir?
Okay, so we're doing all this just to get around the equation, right?
Yes, to get around, right, so the whole point of this, and let's just reinforce that, the whole point of this is we're collecting a series of differentiation rules, so we don't have to keep doing that limit of the difference quotient, because that gets real old real fast. And it would be, some of the stuff we're going to do very soon, it would get really beyond old. It would get so cumbersome that it may not even be doable, right? So we think of that whole process of taking the limit of a difference quotient. That's important conceptually because it explains the way a derivative works, right? And you're thinking the picture I drew on the board, right, that you'll draw for yourself when you're studying for a test or something, which is you're taking the difference quotient, right, the 2 points that define a secant line, and you're going to take the limit as you migrate one point back to the other point and turn that into a tangent line. So you take the slope of the secant line, in the limit becomes the slope of the tangent line, which is the meaning of a derivative. So it's important conceptually that that's how we do it, but we're never doing it again, right? We're always going to just use our rules because they're so much easier and more efficient to use, right? I wouldn't say we'll never do it again, but rarely would we ever do that again, okay? The rest of the year, the only time we'll do it is when we review, probably. That's it, you know. Okay, so what does this give us then? If we differentiate term by term, what's going to be the derivative of the first term? So I bring the 4 down. 4 over 2 is 2, so negative 2x cubed. How about this term? Plus 9x squared. And then finally this guy. Well, how are we going to rewrite that one? X to the 1/2. And so what's that going to give us? 1/2 x to the negative 1/2, which is the same thing as negative 1 over 2 times the square root of x, right? Because the x to the minus 1/2 pushes it to the bottom, and x to the 1/2 is just a square root. So we could, if we want to write it in terms of a square root, there it is. Okay? Moral of the story being, we can just differentiate term by term. So there it is. This is what we call the sum and difference rule. Not that that matters. If we take the derivative of f of x plus or minus g of x, we just separate that into f prime of x plus or minus g prime of x. Okay? All right, so what's next here? We doing, okay, so we'll find a peek. We got a little time. This is one we could prove real easily. So if we want to do, let's try to figure out, it's good to go through some proofs. So what if we're starting with the function f of x equals sine x, and we want to come up with the derivative of that? Okay, let's go ahead and,
Well,
do this one once using limits to build the rule, and then we'll just use the rule from there, right? So f prime of x equals limit of x plus delta x minus f of x over delta x. This delta x goes to 0, which becomes, for our function, what? What's f of x plus delta x if f of x is sine x? Sine of x plus delta x, right? Minus f of x would just be sine x over delta x. Delta x goes to 0. So how are we going to simplify this one, do you suppose?
Yeah, expand that.
Yeah. Yeah, we just expand sine of a sum, right? And so that one is, do you remember it? Sine of x plus delta x would be sine x cosine delta x plus cosine x sine delta x, right? Minus sine x all over delta x. I'll give you 30 seconds to see if we can come up with a plan on this. So I'll lead you into it a little bit. Think about now the argument of the limit, the things that's changing. The thing that's changing is the delta x, right? So we have some special trig limits. You want to think in terms of those, right? So the theta in this case is a delta x, if that makes sense. You see a way you can group this up so that we're going to get limits that we know. If I try to evaluate it directly, I'm getting 0 over 0, for sure. Remember, I can collect these terms separately, right? I've got a common denominator, but I can split the fractions up and make that 3 separate fractions or 2, whatever I want. What do you think?
So the first term would be sine x times 0.
Well, yeah, but, so every term is going to go to, I'm going to end up with, actually it's sine x times 1, right? So if I try to evaluate it directly, I'm just going to get 0 over 0, which means more work. But what's the more work look like is what I'm asking you.
What is that, so it's sine x, cosine x over delta x. Well,
Okay, so let's split it up. Okay, and while we're splitting it up, do you see any one of those terms on top that's going to go particularly well with the one on the bottom?
sine x is over delta x.
Meaning this one right here? Because I've got the sine of delta x over delta x. So let's take this term by itself. We already know what that one's going to be. What does that limit go to? 1, right? So that's giving us a cosine x. That's pretty good. Now what's left over? Look at all the other stuff that's left over here. This will be our red one. So that's trying to be something too, isn't it? What if I factored out, I'm just going to speed this up a little bit. What if I factored out a negative sine x from those other two terms? So I get minus sine x. What's left over if I do that? This one's going to give me a 1. This one's going to give me a minus cosine delta x. And I've got my common denominator of delta x on the bottom, right? Because I split up these terms separately, so they each get the common denominator, right? That's a limit we know too. What's that one? Yeah, that one goes to 0. And so I end up with, my final answer just looks like cosine of x times 1 minus sine x times 0, so it's cosine x. How about that? So the limit of sine x is cosine x, or the derivative of sine x, sorry. Derivative of cosine x, we could do the very same thing, and what we find is that it's oh, that's backward, I've messed that up. Fix that. No, that's supposed to be the derivative with respect to x of cosine x equals negative sine x. Okay? Yeah, go back. Okay. Okay? So it's just kind of a cool little proof. I mean, everything falls into place. But it's a proof involving some trig stuff. Those are good to see. Okay, so we've added some other things then. Okay, I'm going to give you another one for free. I'm not even going to bother trying to, it's not hard to prove, but here's the easiest function to differentiate. The derivative of the exponential function e to the x is e to the x. That's pretty bizarre. Think what that's saying. Very cool. If you graph an exponential function, so there's y equals e to the x, how crazy is that? That any x value I pick, the value of the function is e to the x. What's the slope? E to the x. That's crazy, right? The slope always equals the value of the function no matter where you evaluate it. Pretty crazy. But that's one way to think of the definition of an exponential function, as a locus of points that meets those criteria.
So we can change E, right? It's not
No,
necessarily.
you can't. No, this is e. This is the exponential function, e to the x. Yeah. So this is specific to it. Later on in the year, we'll come back and we'll look at ways that we can combine that derivative form with our knowledge of the properties of logs and exponents to come up with some other things too. But not today. We'll push that out a little bit. That won't be in Unit 2. Okay. Okay, so let's practice with this stuff a little bit. So let's do a couple examples. So what if we have f of x equals 3 e to the x? The derivative is stupidly simple. What's the derivative? If we have f of x equals x squared plus e to the x, what's f prime of x? If we have f of x equals sine x minus e to the x, what's f prime of x? There you go. Okay. Make sense? Okay. All right, so next thing we can do then, next thing would be, let's take advantage of these rules that make taking derivatives so easy, and let's do something with the derivative. Now this is, first assignment pretty much just covers, just practice using the rules. That's it. So that's the assignment for tomorrow. And it's like 15, they just go very fast. Just get some practice with these things. Next issue would be, what if we want to do something like, let's say we want to find, so let's find the line tangent to the curve, f of x equals 3x squared minus the square root of x, and x equals 4. So really, this is, what's the calculus going to do for us here?
It's gonna find us the slope.
It's going to find us the slope. Once we find the slope, it's algebra 1, right? Then all we need, if we've got a slope and a point, it's easy to build a line, right? So how are we going to get the slope then? Okay, we're going to take the derivative. So we got to come up with the derivative function. What's that going to give us? What's the derivative of the first term going to be? Gilsdorf, what are we going to get when I differentiate 3x squared? 2 times, like
Wait.
6x, good. How about the square root of x? Do we remember what that was? It's x to the 1/2, right?
Or 1 over 2.
Good. So it's 1/2 x to the minus 2, which would be 1 over 2 root x. Good. So we need a point and a slope, right? So what's our point of tangency going to be?
Point
point of tangency is gonna be, what's the x value gonna be? 4. What's the y value? How would I, rather than tell me an answer, how am I gonna know what the y value is? Plug it into the function, right? So f of 4 equals 3 times 4 squared minus the square root of 4, which is what, 48 minus 2, so 46. Okay, so we end up with the point of tangency.
Yeah.
What's that?
You're gonna define the point.
Yeah, I'm trying to find the point of tangency, right, so we're plugging it into the original function, okay? So if we want, so there's the point of tangency. Now, the other ingredient that we need is the slope of the tangent line. Well, the slope of the tangent line is going to be the derivative evaluated where? At 4, right? I want at the point of tangency, which has an x value of 4, I want the value of the derivative. So that's going to equal 6 times 4 minus 1 over 2 times the square root of 4. So what is that, 24 minus 1/4? So, yeah, it's actually be 95/4. Okay, so we got the slope. So now all we gotta do is put those together and do it in a line, right? And honestly, on the AP test, this is all you'd have to do. All we'd have to do is say y minus 46 equals 95/4 times x minus 4. Right? Remember that form, point slope form? We don't really emphasize that in the algebra classes, but I probably should have, I guess, in hindsight in honors algebra too, because that's the way we can leave it that way on the AP test. It's really simple though. Point slope form. Point slope is just y minus y1 equals m times x minus x1, where x1, y1 is a point, and m is the slope. And you can just leave it like that. It'd be easy from there. It's easy to distribute and add 46, but that's sufficient. That defines the line. Okay? Make sense? Okay. The only difference with that, what if I change this, and a lot of times these questions will go together. What if I said also, we want the normal line? What's the normal line? The perpendicular, right. It's the normal line, by definition, is the line that's perpendicular to the tangent line. Okay? When that, like later on in college calculus, when you're doing really our class is just calculus of a single variable, right? So when we talk about finding slopes of two-dimensional curves, but when you extend that into multivariable calculus in college, probably be the second or third calculus class too. Then you can talk about, instead of just having two-dimensional curves, you could have a three-dimensional surface, and you talk about the tangent to a three-dimensional surface, what you might call the fall line. So like you're skiing down a slope, where would you point your skis to go straight down the slope? That defines it, at that instant right there, that defines the tangent to the surface, right? And the normal line would just be, where would you drive a stake into the ground, so it's at the base of the stake, it's perpendicular to the ground, right? So you can expand this. And then you could even do things that are non-physical. I mean, you could do this, you wouldn't even have to limit yourself to 3 dimensions. You could do this for 4 or 5 dimensions. It just wouldn't make any physical sense to you, but the calculus would still work, right? Okay, questions? All right. It's probably a good place to stop, I think, huh?